Okay, the next topic is work energy methods, but now for rigid bodies. Okay, so recall we had the following work energy relationship, which we wrote in various different ways. Something like K initial plus PE initial, kinetic energy initial plus potential energy initial, plus work done by other forces. And when we said other forces, forces not accounted for in potential energy, forces other than gravity or springs for our purposes, equals KE final plus PE final. So that's one version, and another version would be KE final plus PE final minus KE initial plus P initial equals work. Or yet another version would just be KE final minus KE initial plus P final minus P initial equals work by other forces. By other forces, we mean not gravity or springs. Okay, so because gravity and springs are essentially taken care of by potential energy changes, is the idea. Okay, so these three equations are basically equivalent. They're just rearrangements of this equation. These two equations are just rearrangements of this equation. And these equations are still true if you have rigid bodies. Rigid bodies. And we can use these equations for the whole system or a single free body diagram. Usually we will be using them for the whole system. Can use these for the whole system, in other words, all rigid bodies or particles, or just the a single free body diagram. Okay. So, but how do these procedures change if you have rigid bodies? The way things change is essentially the expressions for kinetic energy and potential energy. So let's write those things down. If you have a rigid body, for a 2D rigid body, let's say we have some rigid body like so, with some center of mass G. It's got some vertical position yg, and it's got some velocity vg, which could be, let's say, vxi plus vyj. Maybe it's got some angular velocity omega k. If you had such a 2D rigid body, it turns out that the kinetic energy of a rigid body is given by half mass of the rigid body times Vx square plus Vy square. Okay, basically this is, more generally, it's just the absolute value of Vg square. Okay, that's what that is. So I'm not meaning to divide that there. So let's just make sure that that's not the case. This quantity is Vg absolute value square is what I mean to say there. Plus, so this term is true if this object was just a particle at point G, but it turns out because it's a rigid body and it not only translates but also rotates, there is another term in the kinetic energy. It's half Ig omega square. Okay, half Ig omega square. Sometimes people refer to the half mv squared term as translational Ke, and then this is rotational Ke squared. Okay, so this part is sometimes called translational Ke, and this part is sometimes called rotational Ke, rotational kinetic energy. Okay. Anyway, so that's the expression for kinetic energy. It's the same as before for particles plus a term that has to do with rotation of the rigid body. Okay, so that's kinetic energy. That's how things change for kinetic energy. For potential energy due to gravity, is just equal to mass times g times yg. So it's mass times g times yg, where yg is the vertical position of the center of mass. Okay, so this is the vertical position of the center of mass. Okay, so those are the two main changes for using work energy principles. Another one potentially is recall. That's how kinetic energy and potential energies change for rigid bodies. Everything else essentially remains the same. Another sort of little piece that's of use is recall work is of a force F is usually integral F dot dr P acting at P, right, or integral F dot the velocity of point P dt, right, where this quantity is called power. Similarly, if you had a moment, work of a moment, m is integral m d theta, where theta is the angle through which that m rotates the object, and it's also equal to integral m omega dt. So basically you can rewrite this as m d theta equals m d theta by dt, dt, which is basically m omega dt. Okay, so I don't think we're going to be using that all that much, but it's good to know that if work of a force is integral of force dotted with displacement, work of a moment is integral of moment essentially dotted with the angular displacement. Because it's 2D, you can just do everything with scalars. That's it, I guess, for this introductory theory lecture for work energy principles. In the next few videos, we shall look at a few examples of applying these things.